Hello everyone. Title of this video is Solve Rational Inequalities. Alright, so inequalities with fractions involved. Alright. Every exercise I'm going to do in this video, every example, is taken directly from a free online textbook at openstacks.org, and it's their Intermediate Algebra 2nd edition text. I'm in section 7.6, titled Solve Rational Inequalities, and I'll be working on exercises 339 all the way to 370 in this video. So yeah, that's 32 examples, and I will have timestamps for each example in the description of the video. Alright, so example 1 will correspond to 339, example 2 to 340, right, all the way down to example 32 being 370, right? So you just need to, if you want to see a specific one, just count down how many examples it would be and click on that timestamp in the description. Also, I would request that whenever a new example starts in the video, pause the video and try to work on it yourself first before you watch me do it. Because if you're just watching me do it and not working on it yourself, not practicing on your own, you're probably not going to be learning much of anything. Okay. So in every exercise, we're asked to solve the rational inequality, right? Find the solutions, the numbers that you can replace the variable with to make a true statement. And write the solution set, right? Write the solution in interval notation, which you should know about from previous videos or previous sections. Alright. So here's, and I've written out all these examples here. Example 1. Again, this is exercise 339. We're asked to solve this, inequality here. We have x minus 3 in the numerator over x plus 4 denominator is greater than or equal to 0. Alright, so off to the side here, I'm going to write out the steps that I'm following, and these will be the steps I follow for every single one of these examples, all 32 of them. So the first step is to get the inequality in the following form, where I have a single fraction, right, a numerator, a single numerator over a single denominator on one side, and then the inequality symbol, is greater than or equal to, is greater than, is less than or equal to, and then 0 on the other. And it's got to be 0. Alright, so this first example, this is already set up the way I want to start. Single numerator, single denominator, right? A single quotient, a single fraction on one side, and 0 on the other. Okay. The next step, I'm going to find what are now the textbook, the openstacks.org Intermediate Algebra textbook, calls these the critical values. So I'll call them that too. Find the critical values of the variable. Now these values, right? These are just what are the values that make the numerator 0 and the denominator 0. So these are just values that make the numerator of the fraction I have equals 0, and also values that make the denominator equal 0. Alright, so over here in example 1, I have what I want, right? First step's done. Numerator, denominator, one side, 0 on the other. Next, I find what they're calling, the critical values of the inequality. So where is the numerator equal to 0? Well, that would be at x equals 3. And where is the denominator equal to 0? Right, where is x plus 4 equal to 0? And that would be at x equals negative 4. All right, so these are called the critical values of the inequality. All right, the next step. We're going to write these values on a number line and test, to see if they're solutions of the inequality. Right? So I'm going to mark these values or write these critical values on a number line and test if they are solutions. And you always test back in the original inequality. So here's a number line. And this number line will represent, possible values of the variable. And the variable here is x. So I'll put a little x here to let you know that the number line represents, possible values of x. And then I'm going to place the critical values on this line and make sure you're placing them in the correct position, right? That lower numbers are to the left of larger numbers. So negative 4, right, would be to the left of positive 3. All right, so I mark off the critical values and then test them. Test them. Well, negative 4 makes the denominator of this fraction 0. So negative 4 is not a solution. Right, and I'll do the whole testing thing. X equals negative 4. The left side is undefined. And, is greater than or equal to 0. This doesn't make any sense at all. So no. Right? No, not a solution. So to indicate that negative 4 is not a solution of the inequality, I'm going to put a nice big hole or an open point. That's an open point above negative 4. Now how about 3? When I plug in 3 for x, back in the original inequality, we have, 3 minus 3, we have 0 in the numerator divided by 7, right? 3 plus 4, 0 divided by 7 is 0. So I do have 0 on the left is greater than or equal to 0 on the right. And, the equal to part is satisfied, right? 0 is not greater than 0, but it is equal to 0. So this works. Yes. So 3, this other critical value, this is a solution of the inequality. So to indicate that, I'm going to put a nice closed point, a solid dot above 3. So again, open point means not a solution. Closed point means it is a solution of the inequality. It does make it true. Okay. Next step. Now, after you've placed these critical values on the number line, do you see how these critical values break up the number line into pieces, into intervals? You have this interval to the left of negative 4. Right, from negative infinity up to negative 4. You have another interval between negative 4 and 3, and then another interval from 3 to infinity. So what I'm going to do next is test a value in each interval to find intervals of solutions. Test a value in each interval to find the intervals that have solutions. Oops. To find the intervals that have solutions. So once again, here's the inequality. I'll write it here. X minus 3 divided by x plus 4. Right, when is that greater than or equal to 0? And I'll test some values. So first interval is to the left of negative 4. So how about negative 5? Right? X equals negative 5 is over here to the left of negative 4. And if I plug this into the inequality, we'd have negative 8 divided by negative 1 on the left. Well, that's positive 8 on the left. And is that greater than or equal to 0? Yes, it is. It's greater than 0. So this tells me, this leads me to this conclusion here, that this interval to the left of 4, and you can write this in interval notation if you want, that's from negative infinity up to negative 4, but negative 4 we said was not a solution. This is an interval of solutions. An interval with solutions, an interval of solutions, whatever. Okay. And I'll indicate that on my graph here. Right, so all these numbers to the left of negative 4, I'll draw a little mark here with an arrow, should make this inequality true. And you can not, negative 5, negative 6, negative 100, negative 4.1, anything. Go ahead and plug in anything to the left of negative 4, and it should make this true. And I leave it to you to test other values if you wish. Okay, well, what about the next interval, right? That was to the left of negative 4. The next interval is between negative 4 and 3. So I could plug in negative 3, negative 2, negative 1, 0, 1, 2, or negative 3.5, right? 0 is a nice one. How about x equals 0? Now if I plug in 0, the left side is negative, right? We have negative 3/4, right? Is greater than or equal to 0. Is a negative number greater than 0? No. Is a negative number equal to 0? No. Right? So this tells me that this interval between negative 4 and 3, the interval doesn't have solutions. Right? Doesn't have solutions. So I'm not going to write the interval notation for it. Right? There's no point. So nothing there. Right? I'm not putting anything in the graph here in between negative 4 and 3. And then finally, we have the last interval here to the right of 3. So you could plug in 3, 3.1, 4, 5, 6, 7, whatever. Right? A million. So last interval to check. How about x equals 4? That's clearly in the interval. You'd have 1/8. You'd have a positive number on the left. And again, really, you only really need to know if it's positive or negative, right? This was a positive number on the left. This was a negative number on the left. This has a positive number on the left. That's really all you're going to need to focus on, because the other side is 0. Right? The other side of the inequality is 0. And when you're comparing to 0, you only really need to know, am I positive, greater than 0? Am I negative, less than 0? Right? So we have, when I plug in 4 for x, so it's 1/8, a positive number is greater than or equal to 0. Well, yeah, a positive number is greater than 0. So yes, this is a solution. And this interval would be from 3 to infinity, right? These are solutions. But remember, 3 was a solution, we said, right? 3 was a solution. So I got the bracket on 3 and always parentheses on infinities. So this is another interval of solutions, an interval that does have solutions. Great. And I'll mark that off on my picture up here by drawing a little arrow to the right of 3. So all these numbers, to the left of -4 make this inequality true. -4 doesn't, because it makes a denominator 0. Right? Can't have that. The numbers between -4 and 3 don't work, and to go ahead and plug some in, it won't be true. And then 3 works, and every number above 3 will also work. And I've written out the intervals for these solutions, and all we're doing now is doing the union. Remember, when you have multiple pieces of your graph going left to right, you do the interval for one, union will represent a gap or a hole in the graph, and then the interval for the other. All right, so the interval notation for our, which is what they're asking us for, the interval notation for our solutions is, again, left to right, always left to right. So the first interval that had solutions was this interval from -infinity to -4, right, but not including -4, parentheses, right? And then remember the union symbol, right? This represents the gap, the word or, right? The little space between. And then the other interval that had solutions was down here from 3 to infinity, right? 3 to infinity including 3, right? So a bracket on 3. And this is what they wanted from us, right here. A nice description of the solution set in interval notation. Right. And go ahead and check it out. Replace x with any number less than -4. This should work. Replace x with any number that's 3 or greater. And this should also be true. And like I said back on the graph here, any number between -4 and 3 should make this false, right? Shouldn't be a solution. So I like making the little graph on the number line as well as writing the interval notation at the end. But yeah, but these are the same steps I'm going to follow every single time. Every single time. First, I get it in the form where I have a single fraction on one side, one numerator, one denominator. And then the inequality symbol, greater than, less than, greater than or equal to, less than or equal to. And then 0 on the other. No other number but 0. Then I find these critical values. What makes this numerator 0? What makes this denominator 0 for this fraction? And I write these numbers, these critical values, on a number line and test if they're solutions or not. And they get an open point if they're not solutions. They get a closed point if they are solutions. And then those critical values will break the number line up into intervals. And I test a value in each of those intervals to try to figure out which intervals have solutions to the inequality. And it's as simple as all this. No, it's not. I mean, I say it's simple. It's a lot of steps. I get it. But it'll work every single time. All right. Now, one thing I want to point out with inequalities that I find people tend to make a lot of mistakes on. People make this mistake a lot. So again, back to this original inequality here. Inequalities, right? For inequalities, don't, and this is for inequalities with the greater than, less than, greater than or equal to, less than or equal to symbols. Don't multiply by the LCD. I know you're used to this, Remember the least common denominator? Don't do it here. You did it with equations, right? When you had a rational equation, when it was just equals, you could multiply through by the LCD, multiply both sides. But look what happens. So I have x minus 3 over x plus 4 is greater than or equal to 0. The LCD here would be x plus 4. So if I multiply both sides by x plus 4, I'll multiply the left side by x plus 4, multiply the right side by x plus 4. Look at what happens. The issue with this is that because this has a variable in it, you don't know, right? You don't know if you're multiplying both sides by a positive number or a negative number. Remember, this matters. This matters when you're dealing with inequalities. Because if this were a positive number, if x were 1 or 2 or 3, then you could say, hey, the symbol stays, right, the way it is. But if x plus 4 was negative, maybe x were negative 5 or negative 6 or something, then the inequality symbol would flip. Remember, inequality changes direction when you multiply both sides by a negative. So you can do the LCD thing if you break it up into cases. Case 1, when x plus 4 is not negative, the inequality stays, you can do that. But then you have to also go and, case 2, or case 2, sorry, or in case 2, when x plus 4 is negative, the inequality symbol would flip and all that. It's too much of a hassle, right? It's too much of a hassle to worry about the different scenarios, the different cases. So I'm going to tell you, just to make things easier on yourself, for inequalities, don't multiply both sides by the LCD. All right, so I'm going to say no, don't do that. Just leave everything in fractions. I know it's going to stink, right? I know people don't like fractions. Oh my goodness, but it's gonna be better for you in the end. All right, but just for inequalities, right? For equations, you could multiply by the LCD. That was fine. Because for an equation, it doesn't matter if you're multiplying by a positive or a negative. All right, but with inequalities, it does matter, if you're multiplying by a positive or a negative, whether or not the inequality symbol will stay the same or not, or flip over. All right, so that was example 1. All right, again, I'm following the same steps every single time. All right, so next example. Now I've got a couple examples per page for a while. Example 2. Now see how it's already set up the way I want it in the beginning. Got a single fraction, right? Single quotient, one numerator, one denominator on one side. The inequality symbol, this time it's is greater than or equal to, and 0 on the other, right? So this is already the way I want it. Right, the critical values, which I'm just going to label CVs, critical values CV in the future. Well, the numerator is x plus 6, so if x were negative 6, the numerator would be 0. The denominator is x minus 5, so if x were positive 5, the denominator would be 0. Okay, so number line. Now these are possible values of x, representing values of x. Mark off the critical values, right? Negative 6 would be to the left of positive 5. Now negative 6, when you plug that in, you'd have 0 divided by negative 11. You'd have 0 on the left is greater than or equal to 0. Well, the equal to part would be satisfied. So negative 6 is a solution. I put a closed point above that. Now positive 5, on the left side you'd have 11 divided by 0. Right? Remember, you can't have denominators of 0. So 5 is not a good solution. So again, an open point above that, a hole, right, to indicate that 5 doesn't work. All right, then I test some values in each of these intervals, right? You see these two numbers here break up the number line into 3 parts. You have the interval to the left of -6, the interval between -6 and positive 5, and then the interval to the right of 5. So first I'm going to pick a value to the left of -6. Well, how about just -7? So if I do that, if x were -7, you'd have -1 divided by -12. You'd have a positive number, positive 1/12. Again, all that really matters is that it's a positive number. So like in future problems, I'm just going to write, I got a positive number on the left is greater than or equal to 0 on the right. That's how I'm going to write these in some of the future problems. I'll put a plus sign. All right, I've got a positive number on the left, and is that greater than 0? Yeah. All right, so these are solutions. These numbers to the left of -6. All right. And I'll write the interval for that later. Alright, so the numbers to the left of -6 work. How about between -6 and positive 5? Well, again, 0 would be a nice choice, easy choice. Now if I plug in 0 for x, you'd have 6 in the numerator, -5 in the denominator. That'd be -6/5 on the left is greater than or equal to 0 on the right. Again, in future problems, I'm just going to say, hey, we got a negative number on the left side, right? I'll put just a minus sign for negative number is greater than or equal to 0. Is a negative number greater than or equal to 0? No. So these numbers in between -6 and 5 are not solutions to this inequality. And then to the right of 5, how about just positive 6? Right. 6 is to the right of 5. If I plug in 6, I'd have 12 divided by 1, so just 12 on the left is greater than or equal to 0 on the right. Again, later on, I'll just put, I have a positive number on the left, and is that greater than or equal to 0? Absolutely, a positive number is greater than 0. So those are also solutions, right? These numbers to the right of 5, and I'll indicate that with a little marking with my marker here. Right? All the numbers to the right of 5 greater than 5 are also solutions of this inequality. And now that I have the graph of my solutions up, we can put the interval notation pretty easily. Can always left to right for intervals. Right? So I got two pieces here, right? There's a gap, there's a break in it, a hole. So that'll be represented by the union symbol, right? The OR symbol. First interval goes from -∞, comma, up to -6. You're always putting parentheses on the infinities, right? Infinity and -∞ are not numbers. But -6 we said was a solution, so I'm putting that rectangular bracket on -6 to indicate that it is a solution. And we have the gap, right? Union with. And then the interval from 5 to infinity, 5 comma infinity, parentheses on infinity, and we said earlier 5 is not a solution, right, because it makes a denominator 0, and there we have it, right. Here is the interval notation, description of our solution set, all the numbers that I could replace x with and make that a true statement. And there's the graph, right, if they wanted a graph of it, there's a graph of it too. And again, I like making the graph and then writing the interval notation. Nothing wrong with that. All right. Example 3. Same thing. I solve this rational inequality. And it's already set up the way I want. Right? There will be examples in the future in this video where the number on the other side is not 0, and then I have to move stuff, alright? But for right now, it's the way I want it. I got a single fraction, right? One numerator, one denominator on one side is, some symbol is less than or equal to 0 on the other. Always 0 on the other side I want. Alright, then those critical values, right? CVs. This numerator would be 0, right? X plus 1, if x were negative 1. The denominator, x minus 3, would be 0 if x were equal to 3. Right. Then I draw a number line. Alright, this is representing possible values of choices of x here. I mark off where these numbers are, right? We have negative 1 and positive 3, should be to the right of negative 1. And now I determine if these are actually solutions of the inequality. Negative 1 would make the left side 0, and is 0 less than or equal to 0? Well, yeah, it satisfies the equal part. So negative 1 is a solution, right? Put a nice closed point above that. Is 3 a solution? Well, if I plug in 3, I'd have 4 divided by 0, and, divided by 0. Denominator of 0, that's bad, that's undefined. So 3 doesn't work, right? 3 is not a solution, so a nice open point above 3. And then just as in the previous two examples, right, these critical values, they break the number line up into 3 pieces. Right, I've got the interval to the left of negative 1, between negative 1 and 3, and to the right of 3. And I'm going to test a value in each of these intervals and see which intervals have solutions to this inequality. Alright, so let's go from left to right here. Let's start to the left of negative 1. How about negative 2? So I'm going to test x equals negative 2. Now if I do that, the numerator will be negative, and this is where I'm going to start going like this now, right? The numerator will be negative over. The denominator will be negative. So we have a positive number on the left side. I'm going to start just drawing the signs out, because I don't need to know the actual values, right? We are comparing to 0. So all I need to know is if it's positive or negative. That's it. So I have a negative numerator when x is negative 2, a negative denominator, and a negative divided by a negative is positive. So I have a positive number on the left. Is that going to be less than or equal to 0? A positive number is greater than 0, so this is no. So this interval here to the left of negative 1 doesn't have solutions. So I'm going to leave it blank in the graph. Okay, how about between negative 1 and positive 3? Once again, 0 would be an easy choice. Right? Now, 0 is not always possible. If 0 was a critical value, then you couldn't use it as a test value later. Alright, now when I plug in 0, the numerator would be positive. The denominator would be negative. And a positive divided by a negative is a negative, right? So I'm using plus signs to represent positive, minus signs to represent negative. So I have a negative number on the left is less than or equal to 0 on the right. Is this true? Yeah, a negative number will be less than 0. So yes. So this interval between negative 1 and 3 does have solutions. So I mark that off. I indicate that with my marker. And you could test any other number you want, and you'll see any number in here between negative 1 and 3, plug it in, will make that a true statement. And finally, the only other interval I haven't checked yet, greater than 3. Well, how about 4? 4, 5, 6. How about x equals 4? If I plug in 4, the numerator will be positive. 4 plus 1. The denominator will be positive, 4 minus 3. And positive divided by positive is positive. Right? So the numerator will be the left side will be a positive number. And then we have is less than or equal to 0. And is a positive number less than or equal to 0? No, it is not. So the only interval that has solutions is this interval between -1 and 3. So here's the graph of my solution set. And once I have the graph, it should be easy to write up the interval notation for it. Going left to right, this is the interval from -1 to +3. We said -1 was a solution, right, so I got a bracket on that. And +3 is not, so parentheses on that. And there you go. There's the interval notation that they want for the solution set, right? Describing all the numbers I could replace x with and make that a true statement. Wonderful. Alright, so I'm going to speed things up just a little bit because a lot of these examples are very, very similar looking in the beginning here. Alright, so next example. Example 4. It's this is already set up the way I want. Single fraction on one side, 0 on the other. Alright, so first the critical values are x equals 4 makes the numerator 0, -2 makes the denominator 0. Number line, possible values of x, I mark off these. Now -2 would be to the left of 4. -2 would not be a solution because it makes the denominator 0. +4 would be. If I plug in 4, you'd have 0 on the left is less than or equal to 0 on the right, and the equal part is satisfied. So a closed point above 4 to indicate that it is a solution. Then I start testing a value in each of these intervals. All right, to the left of -2, say I plug in -3, you'd have a negative numerator and a negative denominator. So you'd have a positive number on the left. And is a positive number less than or equal to 0? Nope. So no solutions to the left of -2. How about between -2 and 4? Again, x equals 0 is a good test. You'd have a negative numerator, a positive denominator, so you'd have a negative number on the left is less than or equal to 0, and yeah, that would be true. A negative number is less than 0. So these numbers between -2 and +4 work, and I'll mark that off. And then to the right of 4, how about x equals 5? Plug it in, you'd have a positive numerator, a positive denominator, so the number on the left side would be positive. And is a positive number less than or equal to 0? Nope. So those are not solutions. So there's a graph of all the solutions, and when you write out the interval notation for that, that's the interval going from -2 to +4. -2 is not a solution. Parentheses, +4 is a solution of the inequality, bracket. And there's the interval notation they are asking for the solution set. And I leave it to you to test, go ahead and replace x with any number between -2 and 4 or 4 itself, and that inequality should be a true statement. And any number that's not in this set, right, should make it false. Great. Example 5. So again, I have it the way I want. Single fraction, one numerator, one denominator on the left, 0 on the right. And the critical values, CVs, are the values of x that make the numerator and denominator 0. Well, the numerator would be 0 when x is 7. The denominator would be 0 when x is 1. And here's a number line. Possible values of x. I mark off these critical values right now. 1 would be to the left of 7. And then I see if they're solutions or not. Right now, when I plug in 1, the denominator is 0. That's bad. Right? So 1 can't be a solution. So an open point there above 1. When I plug in 7, You'd have 0 divided by 6. You'd have 0 on the left. Now, is 0 greater than 0? No, it's not. 0 is equal to 0, but there is no or equal to symbol here. So when I plug in 7, it's false. We'd get 0 is greater than 0. So 7 doesn't work either. So just an open point above 7 as well. Alright, and then just like the first 4 examples, these critical values break the number line up into 3 pieces, 3 intervals. And I'm going to test each of these 3 intervals. To the left of 1, well, 0 is to the left of 1, so I'll test 0. Again, that's an easy number to test most times. Now, if x were 0, the numerator would be negative, the denominator would be negative, making that a positive number on the left. And then we have is greater than 0. And is a positive number greater than 0? Yes. Yes, it is. So this interval to the left of 1 has solutions. So I'll indicate that with a little arrow there. Now how about between 1 and 7? So let's just take x equals 2. Right, that's between 1 and 7. Now if x were 2, this fraction, the numerator would be negative, right, negative 5. The denominator would be positive, positive 1. So you'd have a negative number on the left, right, a negative number on the left. And is that going to be greater than 0? No. Right? A negative number is not greater than 0. So this interval, right, between 1 and 7, I'm going to leave blank. Doesn't have any solutions. And then to the right of 7, say just 8. Right? X equals 8, I'll choose from there. And if I plug in 8, the numerator is positive, the denominator is positive, so I would definitely have a positive number on the left side. And then we have is greater than 0, and that will be true, right? A positive number will be greater than 0. So I indicate that this interval, right, to the right of 7 has solutions. Mark that off on my graph. So here's our graph, right, a picture of all the numbers that make this true. And notice that there's a break in it, right? So we're going to have that union symbol again, right? Every time there's a break or a hole in the graph, you indicate that with a union symbol. Going left to right, this first interval on the left is from negative infinity up to positive 1. Always parentheses on the infinities. And 1 we said was not a solution. So parentheses on that. Then the space, the gap, the hole, whatever in the graph, I'll represent that with the union symbol. Then the next interval, 7 to infinity, right? It's going from 7 to infinity. And we said earlier, 7 is not a solution, so parentheses on that, and always parentheses on the infinities. And here is your interval notation representation of the solutions of this inequality. Great. All right, so again, pretty quick, these first ones anyway. Example 6. X plus 8 over x plus 3 is greater than 0. It's already set up the way I wish. Single fraction on the left, 0 on the right. So now I want the critical values. We have x equals, now the value of negative 8 would make the numerator 0. And the value of negative 3 for x would make the denominator 0. Here's a number line. Possible values of x. Now negative 8 would be to the left of negative 3. And let's see if there's solutions or not. Now when you plug in negative 8, the left side would be 0, and we have is greater than 0. Well, 0 is not greater than 0. It's equal to 0. So negative 8 is not a solution. And negative 3 can't be a solution either, because negative 3 makes a denominator 0, and you can't have that. That's undefined. So another open point above negative 3. And now these critical values, right, they break up the number line into 3 pieces again, right, since there's only 2 critical values. And I'll start testing numbers. All right, so how about -9? All right, that's to the left of -8 here. Well, if I plug in -9, the numerator would be negative, the denominator would be negative. So you'd have a positive number on the left, negative divided by negative. And is that greater than 0? Absolutely. So this interval with numbers to the left of -8, less than -8 here, are solutions, and I'll mark that off on my graph. Between -8 and -3, how about -4? That's between -8 and -3. Now if I plug in -4 for x, the numerator would be positive, the denominator would be negative, and a positive divided by a negative is negative. And is a negative number greater than 0? Nope. So this is going to be left blank, this interval. No solutions in there. And then I'll just choose 0. To the right of -3, 0's in there. Sure. Just pick a number to the right of -3. 0 is always an easy number to plug in if you can use it. And if I plug in 0 for x, the numerator is positive, the denominator is positive, so I'd have a positive number on the left for certain. And is that greater than 0? Absolutely. So this interval to the right of -3, these numbers greater than -3 are solutions. So again, I indicate that on my graph. So here's a graph of the solutions and then the interval. Again, the first one here would be from -infinity up to -8. Parentheses on both those because neither of those are solutions. Right? Then you have the gap or the hole in it represented with the union symbol, the or symbol. And then the other interval going left to right is from -3 to +infinity. -3 was not a solution, so parentheses on that, and always parentheses on infinities. And here's the interval notation for that solution set, right? All the numbers that I could replace x with to make that initial inequality a true statement. Okay. Example 7. We're almost done with these pretty easy ones. All right. We'll eventually get to ones where we have to do something in the beginning. Because again, this is set up the way I want. Single fraction one side and 0 on the other. And those critical values, right, CVs, the values of x that make the numerator of this fraction or the denominator of this fraction 0. Well, 6 would make the numerator 0. -5 would make the denominator 0. And then I mark these on a number line. So here's the values of x, and -5 would be to the left of 6. And -5 makes this denominator 0, and that's bad, right? So -5 is not a solution, right? I indicate that with an open point. +6 is also not a solution, because when I plug in 6, the left side would be 0, but 0 is not less than 0, right? 0 is equal to 0, so 6 is also not a solution. Got open point there. Okay. Again, 2 critical values. We'll break up the line into 3 pieces, 3 intervals. The first, going left to right here, the first interval I'll check is to the left of -5. Let me just plug in -6. Now if I plug in -6 for x, the numerator would be negative, the denominator of this fraction would be negative, and a negative divided by a negative is a positive. So I would have a positive number on the left, and then is less than 0. Is a positive number less than 0? Nope. So this interval I'm going to leave blank. Now between -5 and +6, again, an easy value, if you can use it, would be 0. When I plug in 0, the numerator is negative, the denominator is positive, So the number on the left would be negative. And is a negative number less than 0? Absolutely. So this interval between -5 and 6 has solutions to this inequality, and I'll indicate that on my graph. And then to the right of 6, say just x equals 7. If I plug in 7, the numerator is positive, the denominator is positive, so the number on the left would be positive, and then you have is less than 0, and is a positive number less than 0? No, it's not. So I leave that interval blank, and here's the graph of all the solutions of this inequality. The only numbers that would make it true are any number between -5 and 6, not including -5 or 6. So that's that in interval notation. That would be the interval from -5 to 6. So -5, 6, and neither one of these endpoints is a solution. So parentheses on both of them. And this is the interval notation for the solution set of that inequality. Great. All right, I have just one more like that. Example 8. Where it's already set up the way I want with a single fraction, one numerator, one denominator on one side, and 0 on the other. So if it's already set up that way, you can just, critical values. Well, -5 for x would make the numerator of that fraction 0. +2 for x would make the denominator of that fraction 0, right? So the critical values are -5 and +2. I mark these off on a number line, right, representing different values of x. -5 would be to the left of 2. And neither of these would be solutions, right? When you plug in -5 for x, you'd have 0 is less than 0, but that's false. So open point above -5, indicating that it's not a solution. And when you plug in 2, you get 7 divided by 0. You're dividing by 0, and that's undefined, right? So you can't plug in 2. So that's not a solution either, an open point above that. All right, then I have the 3 intervals again. Right. So we start testing some values. So to the left of -5, I'll test -6. Now if I plug in -6, the numerator would be negative, the denominator would be negative, making the left side a positive number. And is a positive number less than 0? Nope. Right, so blank, leave that interval blank. Between -5 and +2, again, a nice easy number would be 0 if you can use it. 0's in there. Then if I plug in 0 for x, the numerator is positive, the denominator would be negative. So the number on the left side would be negative. And is a negative number less than 0? Yes, it is. So this interval between -5 and 2, those numbers are solutions. And then to the right of 2, say x equals 3, the numerator would be positive, the denominator would be positive, meaning you have a positive number on the left is less than 0, and that's false. That's not true. So again, I leave that blank. So the only solutions to this inequality are all the numbers between -5 and +2. There's a graph of it, and this would be the interval notation for it, right? -5, 2, and then parentheses on both of these, because both these numbers were not solutions. And that's it. All right. Now here's where we start getting a little different. So look at example 9. See, so far in examples 1 through 8, they had it the way I wanted it to start. Single fraction on one side and 0 on the other. Now look at this one. We have that single fraction, fine. But over here, this is not 0. So I can't jump into what are the critical values and doing all this stuff that I've done in the previous 8 exercises. I want to get it this way. So if one of the sides isn't 0, subtract it, get rid of it, make it 0. So I'm going to be subtracting 1 from both sides. So on the left side we have 3x, the first fraction there, 3x over x minus 5. Then minus 1 is less than 0. And now comes the addition or subtraction part. I want to take this left side now, this subtraction problem, and get this as a single fraction. One numerator, one denominator. So remember, when you're adding or subtracting, you need a common denominator. Well, this first fraction has a denominator of x minus 5. The second fraction, 1 has a denominator of 1. So in order to get the two fractions to have the same denominator, I'm going to multiply 1 over here by x minus 5 in the numerator and x minus 5 in the denominator. And notice it is the quantity x minus 5 with parentheses. All right, now that the denominators are going to be the same, right, that's going to be the denominator of the difference. Right? Remember, when you get a common denominator and add or subtract, that common denominator will be the denominator of the sum or difference. And it's the numerators you combine. The first numerator was 3x minus, and then the second numerator is the quantity, right? You're subtracting all of the second numerator, which was x minus 5. So that'll involve distributing this negative here, or distributing negative 1. And then we have is less than 0 still. And then after all said and done, 3x minus x, we have 2x. And then plus 5 in the numerator. And then x minus 5 in the denominator. And then is less than 0. And this is what I want. This is what we want. We want a single fraction, one numerator, one denominator, right? Not plus or minus some other fraction or some other number. And then on the other side, 0. Once it's like this, then we can work the way I've been working the first 8 examples. I find the critical values. So the values of x that make this numerator and this denominator 0. Now the numerator is 2x plus 5. So the value of x that makes that 0 would be negative 5 halves, negative 2.5. And the denominator, that would be 0 if x were 5. Write a number line. Right, for possible values of x, I mark off the critical values. Now negative 5 halves would be to the left of positive 5. And then I test them. Right, and I'm just going to test them right here. Because all I did was subtract 1 from both sides. This inequality here is equivalent to the original inequality. Now negative 5 halves would make the left side 0. But 0 is less than 0, that's false. So negative 5 halves is not a solution. I put an open point above that. Positive 5, when I plug that in, you get a denominator of 0, which is undefined. That's bad. So 5 is not a solution either. I put an open point above that. And now I have, yet again, 3 intervals to test. And we'll see if we get any solutions. So again, I'm testing back in this inequality here, right? This is the inequality I'm working with now. So I'm going to test first. Pick a number to the left of negative 5 halves. Now remember, this is negative 2.5. So negative 3, that would be fine. And if I plug in negative 3, you'd have 2 times negative 3 is negative 6 minus 5, plus 5 would be negative 1. The numerator would be negative, and the denominator would be negative 8. So the denominator would be negative. So you have a negative divided by a negative, which means the number on the left would be a positive. And then you have is less than 0. And is a positive number less than 0? No. So this interval to the left of negative 5 halves, I'm going to leave blank. There are no solutions there. Then between negative 2.5 and 5, zeros in there. If I plug in 0, the numerator would be positive, the denominator would be negative. So the number on the left would be negative. And is a negative number less than 0? Yes. Yes, it is. So these numbers between negative 5 halves and 5 would be solutions. And then to the right of 5, say just 6, right? I'm going to pick any number to the right of 5. The numerator would be positive, the denominator would be positive, so you'd have a positive number on the left is less than 0 on the right, and is a positive number less than 0? No. So that interval stays blank. And here we go. Here are all the solutions of this inequality, which would also be solutions of the inequality I started with. All right, the inequality I started with, all I did was subtract 1. So this is the same inequality, really, right? And I didn't cancel any stuff, right? And you shouldn't be, and I'll write that out later. You shouldn't be canceling things, because you want the inequalities to actually be equivalent all the time. And now I have all the solutions to this inequality here, and the interval notation, right? This picture is from negative 5 halves to 5. Right, negative 5 halves comma 5, and then parentheses on both, because neither one of those is actually a solution of the inequality. Right? Neither one makes it true. And there you go. There's the interval notation. All right. And we're going to be doing this now, right? We're going to have a number, we're going to have something that's not 0 on one of the sides for the next several examples. Okay. Example 10 is very similar. All right, and now we're starting to get new examples, as I mentioned, where yes, I have a fraction on one side, great, but the other side's not 0. So I can't just jump into critical values and number lines and all that. All right, so same deal here. I first must subtract 1. So we have 5x over x minus 2, and then minus 1, and then is less than 0. Right. And then I want to do a subtraction problem. Now 1 is the same as 1 over 1, right? And I want a common denominator because I'm subtracting, right? Adding, subtracting. So I need to multiply this by the quantity x minus 2. I need to put a factor of x minus 2 in the numerator and denominator. That way, both denominators are x minus 2. And if both denominators are x minus 2, and I'm subtracting, that will be the denominator of the resulting difference. Right? So I have a fraction with the denominator of x minus 2, and the numerators get combined. Right? The first numerator is 5x, and we have minus the whole thing. This numerator would be x minus 2. You're not just subtracting the first term. You're subtracting all of it, right? The entire thing, x minus 2. So this will involve distribution of the negative, and then we have is less than 0 still. Then 5x minus x would be 4x, and then minus negative 2 would be plus 2. Alright, so I have 4x plus 2 in the numerator, x minus 2 in the denominator is less than 0, and now I have what I want. I have a single fraction, one numerator, one denominator, and on one side, and 0 on the other. Now, here's another useful tip that I haven't really had to do yet. But here I notice that I can factor the numerator a little more. So a tip is, once you get a single fraction, factor the numerator and denominator. It'll make finding those critical values a lot easier. Factor the numerator and denominator. Alright, now here's the thing I need you to be aware of though. But don't cancel common factors. The reason for that is I want the inequality I have to be exactly the same inequality as the one I started with. And if you cancel common factors, then all of a sudden you may have changed the inequality, too much from the beginning. All right. I'm not going to get into all the reasons why. Just know, please. Kind of like how earlier I said, don't multiply both sides by the LCD. Don't cancel common factors here. Right? Just things that you would normally do with equations, right? You shouldn't be doing with inequalities. Right? So yeah, so I would factor the numerator here. We have, they have a common factor of 2. This is 2 times the quantity 2x plus 1 in the numerator, and then x minus 2 in the denominator. And there are no common factors. So don't cancel. Don't cancel. Just leave everything as is, and then we have is less than 0. All right, but now I do have what I want though. Single fraction, right? One numerator, one denominator on one side, 0 on the other. And now I work through this the way I've worked through the first 9 examples. Critical values. The values that make the numerator and denominator 0. Numerator is made 0 by -1/2. The denominator would be made 0 by x equals 2. All right, that's kind of why I want factored versions of stuff. Right? When the after you get that single fraction, if you factor the numerator, factor the denominator, stating the critical values should be simple. And I put the critical values on a number line. All right, values of x here, and then -1/2 would be to the left of 2. And then I see if these are solutions of this inequality now, right? And again, that's why I'm not canceling common factors, because there aren't any to cancel here anyway. But I want the inequality I'm looking at to be exactly the same inequality as the one I started with, right? Just a little different looking, that's all. But don't do any canceling, because that'll ruin things. All right, so -1/2. You'd have 0 is less than 0. That's false. So that's not a solution. And plugging in 2 is bad because you have a denominator of 0, so that's also not a solution. So I've got some open points above those. All right, next is checking a value in each interval. Again, back in this inequality that I have here, where I have the single fraction on one side and 0 on the other. All right, so to the left of -1/2, how about just -1? That's easy enough. So in the numerator, you have 2 here. Now 2 times -1 would be -2, plus 1 would be -1. And 2 times -1 would be negative. So I have a negative numerator and a negative denominator. So the left side is a positive number. All right, I end up with a positive number on the left. And is that going to be less than 0? Right? We have is less than 0, and the answer is no. Right? A positive number is not less than 0. It's greater than 0. So this interval to the left of -1/2 is no good. There are no solutions in that interval. All right, next, between -1/2 and +2, 0's in there. I'll use that. If I plug in 0, you'd have 2 times 1, you'd have a positive numerator, and then 0 minus 2, you'd have a negative denominator. So a positive numerator, a negative denominator. So you'd have a negative number on the left is less than 0, right? Is a negative number less than 0? Yes, it is. So this interval between negative 1/2 and positive 2 has solutions, and I'll mark that off. And then to the right of 2, say x equals 3, you'd have 2 times 7, a positive numerator, and a positive denominator. So that's a positive number on the left, and then is less than 0. Right? And is a positive number less than 0? Absolutely not. So that's blank. Right, so now I have a graph of all my solutions, and I can very easily now write the interval. This interval for this picture would be from, the solutions are from -1/2 to positive 2. So I have -1/2 comma 2, and then, open points on the ends, so neither one of them is a solution. Parentheses in the interval notation. And there we go. That's what they want right there. Okay. So example 11 is similar. Example 11. Break this up. So same thing where I have, there's a fraction, sure, but on the other side is not 0. I want 0 over here. So let's get rid of it. Subtract 2. So now I have 6x over x minus 6. Then minus 2 is greater than 0, right? After subtracting 2 from both sides. And again, this is like 2 over 1. And I want to get this to be put together as a single fraction. I want a single fraction on one side, 0 on the other. Well, easy way to get the denominators to be the same, I'd have to multiply this denominator by, x minus 6. The quantity x minus 6. And I would do the same with the numerator. So now I have the following. Both denominators would be x minus 6, so that's going to be the denominator of the difference. Then I have the first numerator minus the second numerator is 2 times the quantity x minus 6, and so I'm distributing -2 this time instead of -1 like in the previous ones. And we have still is greater than 0. Alright, so here 6x minus 2x would be 4x. And then -2 times -6 would be positive 12. So I have 4x plus 12 in the numerator. X minus 6 in the denominator is greater than 0. And this is what I want. Right? This is what I want. A single fraction on one side, 0 on the other. And just like I said, a little tip here. Once you get that single fraction, make it easy on yourself. Factor the numerator and denominator. And the numerator can factor to 4 times the quantity x plus 3. And the denominator is simply x minus 6. Right? That doesn't factor any further. And then we have is greater than 0. And this is the inequality I'm working with right here. I'll put some stars next to it. Right, so almost imagine like we're starting over and I was given this. And again, if there are any common factors, don't cancel them. Don't cancel the common factors because that'll ruin everything. All right, you want the inequality you're working with to be the same equivalent inequality, to the one you started with. All right, so simple enough here. The critical values, CVs, are values of x that make the numerator and denominator 0, which is why I factored. It'll make it easier to find these. -3 for x makes the numerator 0. Positive 6 makes the denominator 0. And then I mark these off on a number line. These are values of x, and then -3 would be to the left of 6. Now please know that, so far in examples 1 through 11, there have been 2 critical values. There can be 1 critical value, there can be no critical values, there can be 5 critical values. Please understand that there's not always going to be two critical values, right? It just so happens that that's the way it's going so far for these examples. Now let's see, -3, is that a solution? You'd have 0 is greater than 0. Nope, that's false. So an open point above -3. And 6 makes a denominator 0, so that can't be good, right? So another open point above that. Now I test some values. So let's bring this paper back up here. Again, we're working with this inequality because it's the same exact one as the beginning, right? Just all I did was subtract 2 from both sides. Didn't cancel anything. To the left of -3, how about -4? Now if x is -4, the numerator would be negative, the denominator would be negative, so you have a positive number on the left. And is that greater than 0? Absolutely. Right. So the numbers to the left of -3 are solutions, and I'll indicate that in my graph. Between -3 and +6, how about 0? The numerator would be positive, denominator would be negative, so the number on the left would be negative. And is that greater than 0? Is a negative number greater than 0? No, it's not. So leave that blank, that interval blank. Then to the right of 6, how about 7? If I plug in 7 for x, the numerator is positive, the denominator is positive, so the number on the left is positive. And then we have is greater than 0, and is a positive number greater than 0? Yes, it is. So the interval here from 6 onward to the right of 6, those are solutions. So here's a picture of all the solutions, a graph, and then interval notation. There are 2 intervals here, right? There's a gap between them. I'll bring in the union symbol. First interval is from -infinity up to -3. Parentheses on both of those, and then a union for the gap, the hole in the graph here, and then the second interval there is from 6 to +infinity, and parentheses on both of those. Right? There we go. Right, there's the interval notation for our inequality there, a description of all the numbers that would make even the original inequality true, right? Because once again, all I did was subtract 2. Right? This inequality here is exactly the same as the original, it just looks a little different. And again, no canceling. Do not cancel common factors, please. Okay. I guess you could cancel common factors if you already listed the critical values, but do it after the critical values. But just to be safe, stick with what I said. Alright, don't cancel common factors, just make it easy on yourself. Alright, example 12. Same thing as the previous examples, right? I've got a fraction on one side, but I don't have 0 on the other. So I'll speed this up a little bit. We're subtracting 2. Alright, so I have 3x over x minus 4 minus 2 is greater than 0. Great, now I have 0 on one side. And what I'd like to do is get this to be a single fraction. Now, I hope you see that they're going to have the same denominator of x minus 4. And the first numerator would be 3x minus the second numerator is going to be 2 times the quantity x minus 4, right? I have to multiply this by x minus 4 over x minus 4. And we have is greater than 0. And then distributing the -2, we have 3x minus 2x would be x, and then -2 times -4 is +8. So I have x plus 8 in the numerator, x minus 4 in the denominator, is greater than 0. And now I just work with this. Right? Again, this is the same inequality as the beginning. All I did was subtract 2 from both sides. And it's what I want. Single fraction, numerator and denominator are totally factored already, is greater than 0, 0 on the other side. Alright, so what are these critical values? -8 and +4. I mark these off on a number line. -8 would be to the left of +4. Neither one would be a solution. Open points, right? If you plug in -8, you have 0 is greater than 0, which is false. You plug in 4, you get a denominator of 0. And then I start plugging in values. Now I'm going to talk this one out here. Alright, you test values. I should write it, I guess. Alright, so -9. Right, just pick a value to the left of -8 here. You'd have a negative numerator, negative denominator, so you have a positive number is greater than 0. That's true. So this interval to the left of -8 has solutions. I'll mark that off. Between -8 and +4, how about 0? You'd have a positive numerator, negative denominator in this fraction here. That's a negative number. Is a negative number greater than 0? Nope. So blank in between those two. And then to the right of 4, how about just 5? Positive numerator, positive denominator, so a positive number. And is that greater than 0? Yes, it would be. A positive number is greater than 0. So any number to the right of 4 should be a solution as well. And then now that I've got my picture, I can write the interval notation. It's be from -infinity to -8 with parentheses on both. In union with, right, the gap, the hole in the graph here, and then 4 to infinity. Parentheses on both. Right. And this is what they're asking for, right? The interval notation. Great. Okay. So again, I'm gonna kind of speed things up in the beginning. Example 13. I'd subtract 1 from both sides. Now, I'm hoping you see the least common denominator is x minus 6. So when I do subtraction, I'm going to have x minus 6 as the common denominator. The first numerator is 2x plus 3. And I'd be subtracting 1 times x minus 6. And this is less than or equal to 0, right? So these are the same inequalities. All I did was subtract 1. And then I'm distributing the -1 here. 2x minus x is x. 3 minus -6 would be 3 plus 6. That's plus 9. So I have x plus 9 in the numerator, x minus 6 in the denominator, and is less than or equal to 0. And this is what I'm working with right here, this inequality now. Right. And it's the way I want. A single fraction on one side, 0 on the other. The critical values, x equals -9 and +6. Make the numerator and denominator 0. Mark these off on a number line. -9 would be to the left of +6. -9 is a solution because you'd have 0 is less than or equal to 0, right? We got the or equal to part satisfied, so I'm putting a solid point over -9. That is a solution. And 6 wouldn't be because it makes the denominator 0. And then I test values in these three intervals broken up by these critical values. To the left of -9, how about -10? The numerator would be negative, the denominator would be negative. We'd have a positive number on the left. Is less than or equal to 0? That's false. Alright, a positive number is not less than or equal to 0. It's greater than 0. So no solutions to the left of -9. Between -9 and 6, how about just 0? Positive numerator, negative denominator. So you'd have a negative number on the left. Is less than or equal to 0? Yes, that is true. So this interval, right, the numbers between -9 and 6 are solutions. I mark that off. And then to the right of 6, say just 7. Positive numerator, positive denominator. We have a positive number on the left. Is less than or equal to 0. That is false. Right, so leave that interval blank. So I've got a picture of all the solutions of this inequality now. Right? And again, if these solve this inequality, they're going to solve the first one because they're the same inequality. All I did was subtract 1 from both sides. And this interval in interval notation, you're going from -9 to +6, right? -9 comma 6. We said -9 is a solution, right? So bracket on that, right? Rectangular bracket. 6 is not a solution, so parentheses on that. And here is your interval notation for the solution set of that inequality. And I'll leave it to you to test. Take any number you want between -9 and 6, plug it in, go back to the original inequality even, and see that it'll make a true statement. Okay. Next example. These are all pretty similar for a while for the next few examples here. Alright, so again I want 0 on one side, so I'm going to subtract 1. So we have 4x. Now both of them, I hope you see the LCD would be x minus 4, so when I'm subtracting, the denominator of the difference is going to be x minus 4. And then the numerator, I'll have this numerator, 4x minus 1, and then minus, 1 times the quantity x minus 4. I'm hoping you see that. Right? You should, like I said, I'm going to make these a little quicker now. You should know how to add and subtract fractions by this point. And then we have is less than or equal to 0, right? I want 0 on the other side. After distributing this -1 here, 4x minus 1x is 3x. -1 plus 4, right? -1 times -4. -1 plus 4 be plus 3. Divided by, and then x minus 4, and is less than or equal to 0. And then I'm going to factor the numerator to this. You have 3 times the quantity x plus 1 over x minus 4 in the denominator here, and no common factors. Again, don't cancel things until after you list the critical values, right? If you want to cancel stuff, list the critical values first though. Alright, please. Is less than or equal to 0. Alright, so I got what I want. Single fraction on one side, 0 on the other. The critical values, right, CVs, are the values of -1 and +4. Mark those on a number line. Right, possible values of x, -1 would be to the left of 4. -1 would be a solution. Right? If I plug in -1, you'd have 0 is less than or equal to 0. The equal to part is satisfied. So a closed point on -1. 4 would make a denominator 0, so you can't use 4. Open point above 4. Alright, now I'm testing values. So how about -2 to the left of -1 here? The numerator would be a negative number. The denominator would be a negative number. So you have a positive number on the left. And is that less than or equal to 0? Nope. And a positive number is not less than or equal to 0. So that interval is blank. Between -1 and +4, how about x equals 0? Positive numerator, negative denominator. So a negative number on the left, is that less than or equal to 0? Yes. So we have solutions between -1 and 4, where 0 came from. Right? And then how about x equals 5, right? For the values to the right of 4, you'd have a positive numerator, positive denominator, so a positive number on the left. Is that less than or equal to 0? Nope. So that's blank as well. So there's a graph of all the solutions of these inequalities. And in interval notation, this is from -1 to +4, right? -1 comma 4. Bracket on the -1, right? -1 is a solution. Parentheses on 4, right? Because 4 is not a solution. And that's what they're asking us for, right? The interval notation for the solution set of that inequality. Alright. So pretty similar here. The only difference is, it's the number 2 now on the other side. So I want to subtract 2. I want to get 0 on the other side. Right? And once again, the denominator is 1, so the LCD would be x minus 4. So when I do subtraction, that common denominator is going to be x minus 4. And we have this numerator, 3x minus 2, minus, and then 2 times the quantity x minus 4. right, when I put them together, is greater than or equal to 0 now. Right, I want 0 on one of the sides. After distributing the negative 2, you got 3x minus 2x is x. Negative 2 plus 8 would be plus 6. X plus 6 in the numerator, and x minus 4 in the denominator, and again we have a 0 on the other side is greater than or equal to 0. Alright, so the critical values, right, CVs, these are the values of x that make the numerator or denominator 0. We have negative 6 for the numerator, positive 4 for the denominator. I put these values on a number line representing possible values of the variable, possible values of x. Negative 6 is to the left of 4. And I test to see if these are solutions. Negative 6, when I plug it in, I'd get 0 is greater than or equal to 0. That is true. So a closed point above that. 4 plugged in would make the denominator 0, which is bad, right? That's undefined, so an open point above 4. And then I test values in these 3 intervals broken up by these 2 critical values, right? So to the left of negative 6, how about we test, just negative 7. The numerator would be negative, the denominator would be negative, so I'd have a positive number on the left is greater than or equal to 0, and that is a true statement. So for any value less than negative 6, we have a solution. So I indicate that with I'm drawing that on my graph, the arrow to the left of negative 6. Between negative 6 and 4, I'll test 0. You have a positive numerator, negative denominator, so I have a negative number on the left, and is that greater than or equal to 0? No. So I leave that interval blank. Then to the right of 4, how about x equals 5? Plug it in, you got a positive numerator, positive denominator on the left, so a positive number on the left is greater than or equal to 0 on the right. That is true. So I do have solutions to the right of 4, and I'll indicate that in my drawing. So here's a graph of all the solutions of this inequality, all the numbers that would make it true. And interval notation, you got this interval, which is from negative infinity to negative 6, always parentheses on the infinities, and a bracket, right, on negative 6, because negative 6 is a solution. Then any gaps or holes in the graph will represent with the union symbol, right, union. And then the next interval is from 4 to positive infinity, parentheses on the 4, and because it's not a solution, and always parentheses on infinities, because infinity is not a number. And there's what they want, right? The interval notation for the solution set for this inequality. Wonderful. All right. The next example is the last one that's like those, right? Where we have something that's not 0 on the other side, and then we'll be halfway done. So again, I want to subtract 2. I want to get 0 on the other side here. Now, common denominator would be x minus 3. So let's put everything over x minus 3 here. First numerator, 4x minus 3, minus the other numerator would be 2 times the quantity, x minus 3. And then this is going to be greater than or equal to 0. After distributing the negative 2, we have 4x minus 2x would be 2x, negative 3 plus 6 would be plus 3. Right? So the numerator is 2x plus 3, denominator is x minus 3. And we have is greater than or equal to 0. And this is what I want. A single fraction on one side, 0 on the other. And then we find those critical values, right? CVs. The values of x that make the numerator and denominator 0 are negative 3 halves, right? Makes the numerator 0, negative 1.5. And positive 3 makes the denominator 0. Mark these off on a number line. Right, these are values of x. And negative 3 halves would be to the left of positive 3. I test if these are solutions. Now when you plug in negative 3 halves, you have 0 is greater than or equal to 0. that's true. The equal to part is satisfied. So negative 3 halves is a solution. Positive 3 is not, because you're dividing by 0. Right? That's undefined. You can't have that. Right? So open point above 3. And then I test each of these intervals in this inequality here. Now to the left of negative 3 halves, say x equals negative 2. The numerator would be negative, the denominator would be negative, so you have a positive number on the left is greater than or equal to 0. Yeah. Alright, that's true. So this interval to the left of negative 3 halves has solutions. And I'll mark that with my drawing. Between negative 3 halves and 3, I'll just choose 0 again. Again, you can do whatever you want. I could do negative 1, I could do 1, 2, 2.5. But 0 is an easy one. And you'd have a positive numerator in this fraction, a negative denominator. Positive divided by negative would be negative. You'd have a negative number on the left is greater than or equal to 0, and that is a false statement. A negative number is not greater than or equal to 0. So I'll leave that interval blank. Then to the right of 3, say I choose x equals 4. Positive numerator, positive denominator, so a positive number on the left is greater than or equal to 0, and that is true. So my solutions are, negative 3 halves and to the left, and all these numbers to the right of 3. So there's a graph of a solution set, and once again we're asked to write it in interval notation. The first interval, negative infinity, comma, up to negative 3 halves, always parentheses on the infinities, and negative 3 halves is a solution, so a bracket on that. Then we have a hole or a gap, a space in the graph, so a union symbol there to represent that, the word or. And then this other interval is from 3 to positive infinity, right? 3 comma infinity, and parentheses on both of those, right? Because again, 3 is not a solution. Great. All right. So the next examples now start introducing inequalities here with fractions, where now maybe a numerator or a denominator will be a quadratic polynomial, right? So far, all my numerators and denominators have been linear polynomials, right, where x to the first power was the highest power. Now we're going to start seeing quadratics, right, where x to the second power is the highest power. But the way you do the problem is no different. So example 17, we already have it now. See how it's already set the way I want? Single fraction, one numerator, one denominator on one side, and 0 on the other. Alright, so I don't need to move anything. But I will factor things, right? So this is the same thing as 1 over, and then x squared plus 7x plus 12, that factors to x plus 4 times x plus 3. And then we still have, is greater than 0. Now that everything's factored in this single fraction, it'll be easy to state the critical values, right? The CVs. Nothing makes the numerator 0. The numerator is always 1. But there are now two values that make the denominator 0, right? X equals negative 4 and negative 3, right? And you can easily tell by the factors. So that's why I recommend factoring things after you get a single fraction. Alright, then I mark these numbers off on a number line. Values of x, and we got negative 4 would be to the left of negative 3. And then I test these. Now both of these make this denominator 0, so that's bad. I can't use either one, so neither one of these is a solution. I'm putting open points above both of them. And then just like all the other ones, we have 3 intervals to check. Right. So x equals, how about negative 5, right? Testing values to the left of negative 4. Now the numerator is always 1, right? So the numerator is always positive. And then the denominator, you'd have a negative factor times another negative factor, right? And that'll be positive, right? Negative times negative is positive. So I have a positive numerator, and if x were negative 5, you'd have a negative times a negative, or a positive denominator. So the left side will be a positive number when x is negative 5. And is that greater than 0? Yes, a positive number is greater than 0. So these numbers to the left of negative 4 are solutions. So I indicate that with the little arrow there. Now between negative 4 and negative 3, negative 3.5 really is the best one, I think. Negative 3.5, right? So that's the first time I haven't used an integer, because there are no integers between negative 4 and negative 3. But negative 3.5 works. Now again, the numerator is always positive. And these denominator factors, if x is negative 3.5, negative 3.5 plus 4 would be positive. But negative 3.5 plus 3 would be negative. Right, so I have a positive numerator, and then positive times negative is negative denominator, and then positive divided by negative is a negative number. So again, you don't need to know exactly what the number is. You just want to know if it's positive or negative because we're comparing it to 0. So when x is negative 3.5, that number on the left will be negative. And then is a negative number greater than 0? Nope. Right, so I'm leaving the interval between negative 4 and negative 3 blank. Finally, to the right of negative 3, an easy one would be 0. Then going back to this original one would be easy. You get positive 1/12 on the left. You have a positive number on the left is greater than 0 on the right. Is that true? Yes. A positive number is greater than 0. So the numbers to the right of negative 3 are also solutions. So I marked that in my graph. So here we have a graph of all the solutions of this inequality, all the numbers I can replace x with to make it true. And we're writing the interval notation for this. So first interval here on the left, you got negative infinity, comma, negative 4. Parentheses on both of those, and then you have a union to represent gaps or holes, union symbol. And then from negative 3 to positive infinity, and once again parentheses on those, right? Negative 3 was not a solution. And this is what they want, right? The interval notation describing all the solutions of our inequality. Great. Yeah, so the next several examples are like this, where you have some sort of quadratic polynomial showing up, so hopefully you know how to factor. I'm assuming you do. That should be chapter 6 material from this same text. Alright, so example 18. Again, it's already set up the way I want, with a single fraction on the left, 0 on the right. It's already the way I want it. But I will do some factoring here, right, just to make it easier to state the critical values, and also easier to check if you have a positive or negative number on the left. X squared minus 4x minus 12. That would factor to x minus 6 times x plus 2. And then we still have is greater than 0. Alright, so now the critical values are easy to see. Right, the values of 6, also negative 2. Both of these values would make the denominator of this fraction 0. And nothing makes the numerator 0, right? It's always going to be the number 1. Alright, then I put these critical values on a number line. So negative 2 would be to the left of 6, and neither one of these are solutions. Right, because both of them make the denominator 0, which is undefined. I can't use them. So I'm putting open points above both of them. Alright, then I'm testing values in these, again, 3 intervals. So to the left of negative 2, how about negative 3? Now the numerator is positive all the time. The denominator, I'd have a negative number times another negative number. So the denominator would be positive. Positive over positive. I'd have a positive number on the left, and is a positive number greater than 0? Yes. So again, I have solutions. I have this interval to the left of negative 2 has solutions. Between negative 2 and positive 6, how about 0? Test that out. Now, going back to the beginning, you see that's 1 over negative 12 if x is 0. That's a negative number on the left. And is that greater than 0, a negative number? Nope. So that interval I'm going to leave blank. And then to the right of 6, say how about 7. Again, factored form would be easy here. Numerator's positive, and if x is 7, you have a positive factor here, positive factor there. Positive times positive is positive, so you have everything's positive on the left. So you got a positive number on the left, and is that greater than 0? Well, yeah, a positive number is greater than 0. So these numbers to the right of 6 are solutions, and I'll mark that off. So here's a graph of our solution set. Great. And I'm just writing the solutions in interval notation. We have from negative infinity up to -2, parentheses on both, union for the gap or the hole in the graph there, and then from 6 to infinity, right, parentheses on both. Wonderful. Right. Okay. Example 19 is not much different. So once again, you already have a single fraction on the left, 0 on the right, like I want. And then we'll do some factoring. Now the numerator is 3. I'm just going to keep it 3. And the denominator, x squared minus 5x plus 4, that would factor to x minus 4 times x minus 1. And then we have is less than 0. Alright, the critical values. Now nothing makes the numerator 0, it's always 3. But the value of 4 and also the value of 1, right, those make the denominator 0. Mark these on a number line. 1 would be to the left of 4. And neither one of these is a solution of the inequality because they make denominator 0. Right? You can't do that. That's undefined. So I put open points above those. Let's test a value now to the left of 1. Easy one is 0 again. Now if x is 0, you'd have a positive number, positive 3/4 on the left. You have a positive number on the left. And is a positive number less than 0? No. So this area is blank, no solutions over there. Between 1 and 4, say how about 2? Now in the factored form, when x is 2, the numerator is always 3, right? The numerator is always positive. The denominator, if x were 2, would have a negative factor times a positive factor. So a negative number in the denominator, positive divided by negative, would be negative. So you'd have a negative number on the left when x is 2. And is that less than 0? Well, yeah, a negative number is less than 0. So I do have solutions in this interval between 1 and 4. And then to the right of 4, say I check x equals 5. You have a positive divided by positive, positive. Everything's positive, so you have a positive number on the left. Is that less than 0? No. So the only solutions to this inequality are numbers between 1 and 4. So I have 1 comma 4, and then parentheses on the 1 and the 4, right, because again they were not solutions. So there's the interval notation for the solution set of that inequality. Okay, so still similar stuff here for examples 20 and 21 and 22 and 23. They're all pretty similar with this number in the numerator and a quadratic in the denominator, a single fraction on the left and 0 on the right. So example 20. Numerator is 4. Denominator factors to x plus 4 times x plus 3. And this is less than 0. The critical values, right, the CVs, nothing makes the numerator 0, but -4 and -3 make the denominator 0. And I'll mark those off on the number line. -4 should be to the left of -3. And neither one of these, again, will be a solution because they make a denominator 0. That's undefined, so open point above both of those. And then to the left of -4, how about -5? Again, -5, -6, whatever you want to the left of -4. Plug that in now. The numerator is positive. for this fraction. And then you'd have a negative factor times a negative factor in the denominator. So a positive divided by a positive. So you'd have a positive number on the left. What we have is less than 0. And is a positive number less than 0? No. So I don't have solutions over here. Now between negative 4 and negative 3, how about negative 3.5, right? Negative 3.5. Now this fraction again, the numerator is positive. If x were negative 3.5, you'd have a positive factor times a negative factor. You'd have a negative number in the denominator. Positive over negative, you'd have a negative number on the left. And is that less than 0? Well, yeah, a negative number is less than 0. So this time, the numbers between negative 4 and negative 3 are solutions, right? So negative 3.5, negative 3.1, negative pi, right? Whatever. Those are all solutions of this inequality. And then to the right of negative 3, right, an easy one would be, you could use negative 2, but how about 0 again, right? 0's over there. And you'd have a positive number on the left. Is that less than 0? Nope. Right, so the only solutions to this inequality are the numbers between negative 4 and negative 3. And the interval notation, right, negative 4, comma, negative 3, always left to right, low to high, and then parentheses on either one of those, because again, neither one of them is a solution. And there's your interval notation for the solution set to that inequality. All right, flying along here, example 21. Same deal, right? I already have a single fraction on the left, cool, 0 on the right. But let's factor this stuff, right? Now the numerator's 2. The denominator, right, one of the factors would have to have 2x, and the other one would have to have 1x, and I'd need a plus 3 here and a minus 5 there, right? That would factor to 2x minus 5 times x plus 3. And you can double check by foiling, see if you get 2x squared plus x minus 15 back. And this is greater than or equal to 0. And now that I have what I want, single fraction one side, everything factored, 0 on the other, we can pretty easily state the critical values, right? The CVs. Now nothing makes the numerator 0. It's always 2. But for the denominator, right, 5 halves, or 2.5, would make that factor 0, so the denominator would be 0. And also negative 3 for x would make the denominator 0. Mark these off on a number line. Values of x here, and negative 3 should be to the left of 5 halves. And again, not just like the previous several examples, neither one of these is a good solution to this inequality because you'll have a denominator of 0. So I put open points above both of them. And then we test a value in each of these intervals. Right. To the left of negative 3, how about negative 4? Now if x were negative 4, right, again the numerator is positive, positive 2. And then this factor would be negative 8 minus, 5 would be negative. You have a negative factor. And then negative 4 plus 3 would also be negative. Right? So you have a positive divided by a positive, right? Negative times negative is positive. So this is a positive number on the left. And then you have is greater than or equal to 0. Is a positive number greater than or equal to 0? Yes. So this interval to the left of negative 3 has solutions. Those are solutions of the inequality. I'll draw that. Between negative 3 and positive 5 halves, easy one to check would be 0. You would have a negative number on the left. And is that greater than or equal to 0? No. So no solutions in this interval. And then to the right of 5 halves. Now 5 halves is 2.5, so how about 3? 3 is to the right of 5 halves. If x were 3, again, you have a positive numerator. This would be positive 6 minus 5. This would be positive. So everything's positive. You have a positive number on the left. Is that greater than or equal to 0? Absolutely. All right, so you have the numbers to the right of 5 halves are solutions. All right, mark that off. So here's a graph of the solutions. And now that I have a graph, right, drawing the interval notation should be simple. First interval, from negative infinity to negative 3, parentheses on both, union for the gap, union symbol, and then the other interval from 5 halves to infinity, parentheses on both, right? Because again, 5 halves and negative 3 are not solutions. There we have it, the interval notation for the solution set of that inequality. Okay. Alright, so next example, actually the next two are very similar. Again, the next three with a number in the numerator of the fraction and a quadratic polynomial in the denominator. And you have a single fraction on one side, 0 on the other, like I want. I'm just going to factor again, right? So over here on the left side we have 6, and then the denominator, one of the factors has to have 3x, the other one has to have x, and I would need -5 here plus 1 here, right? So I got -5x plus 3x for the -2x. Great. All right, is greater than or equal to 0. Alright, so I've factored everything now. I mean, I guess you could factor the 6 to 3 times 2, but there's no point really in factoring just numbers with no variables. Alright, so now we can easily state the critical values, right, the CVs. Nothing makes the numerator 0, it's always 6. And the denominator would be made 0 by 5/3 and -1. Alright, I mark these off on a number line. -1 would be to the left of +5/3. Once again, neither of these would be a solution because they both make the denominator 0. Right? Denominators can't be 0, so I put open points above those. And then we'll test some values in these intervals around the critical values. So to the left of -1, how about -2? So numerator of this fraction is always positive. This would be negative, this would be negative. You have negative times negative in the denominator, you'd have a positive in the denominator as well. Positive over positive is positive. So you'd have a positive number on the left is greater than or equal to 0, and is that true? Yeah. A positive number is greater than or equal to 0. So this interval, these numbers to the left of -1 are solutions, and I'll mark that off. Draw that in. Between -1 and 5/3, about 0. Now if x is 0, the number on the left would be negative. It would actually be -6/5, but you'd have a negative number on the left is greater than or equal to 0, and that's false, right? A negative number is not greater than 0 or equal to 0. Alright, then to the right of 5/3. Now 5/3 is 1 2/3, right? So I could pick 2, right? Positive 2, and I'd be to the right of 5/3. Or just to be safe, maybe pick like 10 or 100 or something. There's something over there. Numerator's positive, denominator factors would both be positive. Positive times positive is positive. Positive divided by positive is positive. Everything on the left side is positive. And is that greater than or equal to 0? Absolutely. So all these numbers to the right of 5/3 would be solutions of this inequality. And there's a graph of the solutions. And once you have a graph, writing the interval notation should be a piece of cake. Right? So we have from -infinity up to -1, parentheses on both of those, a union for any hole in the graph, right? Union for the gap. And then from 5/3 to +infinity, parentheses on both of those. There's the interval notation for the solution set of that inequality. Great. Next example, very, very similar. The only major difference, I guess, or minor difference, would be the number in the numerator is always negative now, right? It's a -2, but I do have what I want, right? Simple fraction on one side, 0 on the other. So let's Let's do the factoring. You got negative 2 in the numerator. And the denominator, yeah, so this would factor to, you have 3, you could have 6x and x, but I see it as 3x and 2x to make 6x squared. And minus 2 here, minus 3 there, right? There's your minus 9x, minus 4x for the minus 13x, and then positive 6. Right, we still have is less than or equal to 0. Alright, so now that everything's factored, right, single fraction on the left, 0 on the right, everything's factored, we can easily state the critical values, right, the CVs. Nothing makes the numerator 0, it's always negative 2. But there are values that make the denominator 0, and that'd be positive 2/3 and positive 3/2. So it's like 0.6666666 forever, and this is 1.5. Right. So putting these on a number line, 2/3 is less than 3/2, right? So 2/3 show up to the left of 3/2 on the number line. And once again, as in the previous several examples, neither of these numbers would be a solution because they make denominators 0, right? So open points above both of these. And then I test some values. Now, to the left of 2/3, zeros to the left of 2/3, that's always an easy one to check. Now, if x is 0, going back to the original, you'd have a negative number, negative 2/6 on the left side. You have a negative number on the left side. And is that less than or equal to 0? Right, less than or equal to 0? Well, yeah. A negative number is less than or equal to 0. So, yeah. So the interval to the left of 2/3 has solutions. Now, how about between 2/3 and 3/2? And like I said, this is 0.6666666, 6 repeating. This is 1.5, so 1 is a nice number between 2/3 and 3/2. I'll choose x equals 1. And looking at the factored form here, the numerator would be negative, right? The numerator is negative all the time. If x were 1, 3 times 1 is 3, minus 2 is positive, right? So that's a positive factor there. And then 2 minus 3 would be a negative factor. So I have a negative numerator, a negative denominator, positive times negative, and that's a positive number. So if x were 1, the expression on the left would be a positive number, and then we have is less than or equal to 0. And is that true? Is a positive number less than or equal to 0? Absolutely not. So no solutions are between 2/3 and 3/2. And then to the right of 3/2 would be 2, 3, 4, 5, whatever you want. X equals 2 would be to the right of 3/2. Again, you have a negative numerator. Both the factors in the denominator would be positive, so you have a negative numerator, positive denominator. That's a negative number on the left. And is that less than or equal to 0? Well, absolutely. So the numbers to the right of 3/2 are solutions as well. So here's a picture of all the solutions of this inequality, and then in interval notation we have from negative infinity up to 2/3 for that piece of the picture, parentheses on both, a union for the gap, and then the other piece of the picture, right, from 3/2 to positive infinity, parentheses on both. Right? And there we have it. Right here is the interval notation for the solution set of that inequality. Okay, 24 is the last one that's like these, where you have a number in the numerator of a fraction and then some quadratic in the denominator. And it's a single fraction on one side, 0 on the other, like I want. I'll do some factoring. Right, so the left side here we have negative 1 in the numerator, denominator, so 5x, 2x, then I need plus 3 here, minus 2 here. The 10x squared plus 11x minus 6 would factor to 5x minus 2 times 2x plus 3. Right, because you got 15x minus 4x, 11x, and minus 6. Great. And then we have, is less than or equal to 0. Now everything's factored. The critical values should be easy to state, right? The CVs. Nothing makes the numerator 0. 2/5 would make the denominator 0, right? 0.4. And negative 3/2, right? Negative 1.5. Put these on a number line. These are possible values of x. Now negative 3/2 would be to the left. Positive 2/5, right? And once again, neither of these would be a solution of the inequality because they make a denominator 0. So open points on both of those. Now we test some values. To the left of negative 3/2, like negative 2 would be fine. Anything to the left of negative 1.5. Now, if x were negative 2, on the left side here, this fraction, the numerator is negative. Then you'd have a negative factor, right? Negative 12 times another negative factor, negative 4 plus 3, right? If x were negative 2. So you have a negative numerator, and you'd have a positive denominator, making this a negative number on the left side. And is that less than or equal to 0? Yes, it is. A negative number would be less than or equal to 0. So these numbers to the left of negative 3/2 are solutions, and I marked that on my graph. A little arrow there. Between negative 3/2 and positive 2/5, how about 0? That's an easy one. Now if x were 0, you'd have a negative numerator, negative denominator, you'd have a positive number on the left. And would that be less than or equal to 0? No. So this interval has no solutions to this inequality. And then to the right of 2/5, how about just 1? That's an easy one, or 2 or 3 or whatever. This is 0.4, so 1 or 0.5 even, right? Whatever you want. Anything to the right of 2/5. Just plugging in 1. Now you always have a negative numerator, and then you have two positive factors in the denominator. So you have a negative numerator, positive denominator. That would be a negative number on the left. And is that less than or equal to 0? Yes, it is. So the numbers to the right of 2/5 are solutions. So here's a picture of the solution set. And then the interval notation, very simple, right? First interval here from negative infinity up to negative 3/2. Parentheses on those, a union symbol for the gap. And then the other interval, 2/5 to infinity, and then parentheses on those. And there's the interval notation for the solution set of this inequality. And I leave it to you to test if you want. Test values over here, they should make it true. Test any value in here, it'll make it false. All right. So the last several examples, we have had, fraction on one side, single fraction, 0 on the other. Now we're going to get into examples where we don't have 0 on one of the sides, and I would like to get 0 on one of the sides. All right, so 25. So you see this doesn't have 0 on one side. I want 0 on the right, just a personal preference. So what I'm going to do is I'm going to subtract this 5 over x from both sides. So now on the left side we have 1/2 plus the 12 over x squared, then minus the 5 over x, and is greater than 0, right? All I did was subtract, so the symbol doesn't change, is greater than 0. And then just as before, right, we've done this before earlier in the video, this is not a single fraction, right? I want to put these together. And this is just a bunch of addition and subtraction. Right. So I need a common denominator. Now I'm hoping you can see that the LCD here, the least common denominator, would just be 2x squared. Now remember what I said earlier, for inequalities, don't multiply by the LCD, because you don't know if you're multiplying by a positive or a negative. No, I mean this one would never be negative, but don't worry about that crap right now. I just want to get this all together as a single fraction. Get the same denominator. So in order to get this denominator, 2x squared, the first fraction I'd have to multiply the numerator and denominator by x squared. Alright, that would give me 2x squared in the denominator. Second fraction, I'd have to multiply the numerator and denominator by 2, right, to get a denominator of 2x squared. And the third fraction, the 5 over x, I'd have to multiply the numerator and denominator by 2x, right, to get a denominator of 2x squared. So now, putting all these together, there's a denominator of 2x squared, right, that's going to be the denominator throughout, right, and when you add or subtract, the common denominator stays. And then the numerators, when I combine those, you have 1x squared plus 24, I'll put that at the end, and then minus 10x, I'll put that in the middle here. So now I have what I want. Now I have a single fraction, one numerator, one denominator on one side, and 0 on the other. We still have is greater than 0. And then, as I mentioned much earlier, once we get that single fraction, let's do some factoring. This numerator can factor. That's x minus 6 times x minus 4 in the numerator. And the denominator is, 2 times x, right? Or 2 times x squared, I'll just leave it as x squared, is greater than 0. All right. And now that things are factored, this is what we're working with now. I'm working with this inequality right here. Okay. We can list the critical values very easily. Right? The numbers that make the numerator 0 would be 6 and 4. And the only number that makes the denominator 0 would be 0. So hey, finally, we have come across a problem that doesn't have just 2 critical values, but this one has 3. And then just like the others, here's a number line. And I'll bring up a new piece of paper, and these are possible values of x. Again, the variable is, again, x. And just make sure you're putting these critical values in the proper places. 0 would be to the left of 4, and 4 would be to the left of 6, right? So I mark the critical values off, and then we determine, are these solutions of the inequality? Well, plugging in 0 is bad, because you divide, that makes a denominator 0, so that's not a solution. Put an open point above that. And 4 and 6, if you plug in 4 or 6, you're getting 0 on the left side is greater than 0. Is 0 greater than 0? No. 0 is equal to 0. So 4 and 6 both make the statement false as well. All right, so open points above all 3 of those. Now, because there are 3 critical values, you see the number line is broken up into 4 pieces. I am now testing 4 intervals, 4 values in this inequality here, right? The one I put the 3 stars by. Alright, so to the left of 0, how about x equals negative 1? You'd have a negative factor. You'd have a negative factor multiplied by another negative factor in the numerator. The denominator is always going to be positive. When you square stuff, it's positive. So you're going to have a 2 times a positive. The denominator is always going to be positive because it's something squared. The numerator is negative times negative, that's positive. And a positive divided by a positive is a positive number. So I have a positive number on the left is greater than 0. And is this true? Is a positive number greater than 0? Yeah. So all these numbers to the left of 0 are solutions of this inequality. Okay, now how about between 0 and 4? Between these critical values? Well, 1, 2, 3, whatever you want. I'll take 1. When I plug in 1, you have a negative factor times a negative factor divided by a positive again. So it's the same thing. You have a positive number on the left is greater than 0. So yeah, there's solutions there as well. So between 0 and 4, there are also solutions. So I mark those off. How about between 4 and 6? Well, how about an easy number to pick in there would be 5. Now, if x were 5, you would have a negative factor times a positive factor in the numerator, right, if x were 5. And again, the denominator is always positive. This is a negative divided by a positive, which is a negative number. You have a negative number on the left is greater than 0. That's not true. Right? A negative number is not greater than 0. So this interval between 4 and 6 doesn't have solutions. I'm going to leave it blank. And then to the right of 6, x equals 7, say, you have a positive, positive, positive. Everything's positive. A positive number is a positive number greater than 0? Absolutely. So to the right of 6 are solutions as well. So every number is a solution except for 0, 4, and 6, and all the numbers between 4 and 6. Alright, now this graph, maybe the interval solution, interval notation might be a little trickier, but remember, every time there's a hole in the graph, or a gap, you're using the union symbol. So up to the first hole here, we got from negative infinity to 0. Always parentheses on the infinities, and 0 is not a solution, we said, so parentheses on that. And then you see there's a hole in the graph. Yeah, I know I connected it with there's markings here, but there is a gap in the graph, a hole in the graph here at 0. So I indicate that with the union symbol. Then the next piece of the graph, up until the next hole, the next gap is from 0 to 4 here. So I got 0, 4. And then 0 is not a solution, parentheses. 4 is not a solution, parentheses. And then there's another gap. So another union symbol. And then this last piece of the picture, the solution set, go from 6 to infinity. And 6 is not a solution, parentheses on that, and always parentheses on the infinities. All right, so here is the interval notation for the solution set of this. You can plug in any value of x less than 0, any value of x between 0 and 4, or any value of x greater than 6, and our inequality, even back to the original one. This inequality will be a true statement. And I leave it to you to check out some values, test your own values if you want. All right. So yeah, so the next example is pretty similar to this, the next few of them. All right. So here's example 26. Once again, I don't have 0 on one of these sides, so I'd like to get that, right? So I'm just going to subtract this fraction here. So on the left side we have 1/3 plus the 1 over x squared, then minus 4 over 3x, and then is greater than 0. Right. And then I'd like to put these together. We're adding and subtracting, so I need a common denominator. Right? The LCD, the least common denominator here, I'm hoping you see was obvious, would be 3x squared. So this first fraction I'd multiply by x squared over x squared. Second fraction I'd have to multiply by 3 over 3. Third fraction I'd have to multiply by x over x, right? So that way every denominator is 3x squared. Right? Now that they all have the same denominator, that's going to be the denominator of the sum. Then you're just combining the numerators for the numerators. So I have 1 times x squared, which is x squared, plus 1 times 3 is positive 3, so I'll put that at the end, plus 3, because it doesn't have a variable, right? And then minus 4 times x, I'll put that in the middle, minus 4x is greater than 0. And then now I have what I want. I have a single fraction on one side, one numerator, one denominator, 0 on the other. Do some factoring, right? The numerator can factor. The numerator factors to x minus 3 times x minus 1. Denominator is just 3x squared. Okay, so this off to this side over here. The critical values, the values that make the numerator 0 are 3, and 1. And the only value that makes the denominator 0 is 0. So here it is again, another example where there are 3 critical values. Right? So there's a number line representing possible values of x. Put these in the right order. 0 should be to the left of 1, and 1 should be to the left of 3. Right? And once again, none of these are solutions. 0 makes the denominator 0 of that fraction, so that's undefined. That's no good. So I put an open point above that. And then 1 and 3, they make the left side 0. That's fine. But is 0 greater than 0? No, it's not. Right, 0 is equal to 0. So neither 1 nor 3 are actually solutions to this. Right. Then we test some values. So x equals, let's say, -1, right? That's to the left of 0. You'd have a negative times a negative. Should be positive numerator and a positive denominator. You'd have a positive number is greater than 0, which is true. So we have solutions to the left of 0. Now how about between 0 and 1? So how about x equals 0.5 or a half, or 3/4 or 2/3, something between 0 and 1? You'd have a negative times a negative. You'd have a positive again divided by a positive. You'd have another positive number on the left is greater than 0. Absolutely. So all the numbers between 0 and 1 are also solutions. I marked that off. Between 1 and 3, how about 2? You'd have a negative times a positive, which is negative numerator, positive denominator. You would have a negative number on the left. And is that greater than 0? No, it wouldn't be. So the numbers between 1 and 3 are not solutions. And then to the right of 3, say x equals 4. Positive, 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 everything positive on the left. Is that greater than 0? Yeah. So the numbers to the right of 3 are all solutions. So we have lots of solutions, right? Everything except for 0, 1, and 3, and everything between 1 and 3. Those are the only ones that are not solutions. Alright, then the interval. First interval up to the first hole here. Be -infinity up to 0, and then parentheses on both of those. And then a union representing a hole or a gap in the graph. Then the next piece of the picture is from 0 to 1, so 0, 1, and neither one of those are solutions, so parentheses on those. Then we have another hole or a gap in the graph, so another union symbol. And then the next piece, the last piece of the picture over here, from 3 to infinity, parentheses on 3 because it's not a solution, and always parentheses on the infinities. And here it is, the interval notation for the solution set to that inequality. Okay, 27. Same kind of problem. So once again, I'm going to subtract 1 over x, get 0 on one of the sides. So we have 1/2 minus 4 over x squared, then minus 1 over x is less than or equal to 0. So I've got 0 on one side. Now I want a single fraction on the other. So again, I'm going to do some subtraction here, some addition, right? We need a common denominator. Now I hope it's easy to see again that the LCD is just 2x squared. So this first fraction I'd have to multiply by x squared over x squared. Second fraction I multiply by 2 over 2. Third fraction I multiply by 2x over 2x. Alright, that way all the denominators are 2x squared. And if all the denominators are 2x squared, I can put them together, right, and that 2x squared will be the denominator of the difference. Then we're just combining the numerators. 1 times x squared is x squared. -4 times 2 is -8. That'll be at the end here. Let's put it there. And then -1 times 2x is minus 2x. Right, so there's the numerator, x squared minus 2x minus 8. Denominator 2x squared. And then we have, now we have what we want. I have single fraction on the left, 0 on the right. Let's do some factoring over here. The numerator factors to x minus 4 times x plus 2. Denominator is just 2x squared. It's less than or equal to 0. And off to the side here, the critical values, right, the CVs. the numerator is made 0 by positive 4 and negative 2. And the denominator is made 0 by 0. So once again, I have these three critical values, which I'll mark on a number line here. Negative 2 would be the farthest left, then 0, then 4. Now, plugging these in. 0 would be bad because it makes the denominator 0, right? So 0 is not a solution. I put an open point above that. But negative 2 and positive 4, both of those make the left side 0. And is 0 less than or equal to 0? Yeah, it satisfies the equal part. So negative 2 is a solution, close point above that. Positive 4 is a solution, close point above that. Right. And now I test the value in each of these four intervals. All right, so when x is negative 3, right, some value to the left of negative 2. Looking at the factored form here, we'd have a negative times a negative, so a positive numerator and a positive, because you're squaring times 2 there, denominator. Everything positive. Is a positive number less than or equal to 0? Nope. So no solutions to the left of negative 2. Between negative 2 and 0, how about negative 1? That's between negative 2 and 0. If I plug in negative 1 for x, we'd have a negative times a positive, which would be negative, divided by positive. Negative divided by positive is negative. You'd have a negative number on the left is less than or equal to 0. That is true, right? Yes. So the numbers between negative 2 and 0 work in this inequality. So I marked that off in the graph there. Between 0 and 4, how about 1, positive 1? Now if x were positive 1, you'd have a negative times a positive. You'd have a negative in the numerator, positive in the denominator. So you have a negative on the number on the left side is less than or equal to 0. That's also true. So all these numbers between 0 and 4 also satisfy the inequality. And then how about to the right of 4? Let's pick 5 here. Well, everything would be positive. You'd have positive on the left is less than or equal to 0. That's false. So the only solutions are, every number from negative 2 up to 4, just not 0. Just not 0. So there is a hole in the gap. Right? There is a hole in the graph. There is a gap. So I will be using a union symbol here. So going left to right, the first piece of the picture up to the first hole, the first gap, is from negative 2 to 0. Right? So negative 2 comma 0. Bracket on negative 2, right? It is a solution. Parentheses on 0 though. Right? It's not a solution. Then I have a hole in the graph, a gap. So a union symbol. And then the next piece of the graph, after the gap, is from 0 to 4. Parentheses on 0, right, it's not a solution, and a bracket on 4. And there's the interval notation describing the solution set of this inequality. Wonderful. All right. Example 28 is pretty similar to this. So once again, I would like 0 on one side. So I'm going to subtract this 1 over x. So I got 1/2 minus the 3 over 2x squared, and then minus 1 over x is greater than or equal to 0. So I've got what I want on one side. I've got 0 on one side. Now I'd like to make the other side a single fraction by adding and subtracting. So I need a common denominator. Again, it's obvious here to me. I hope it's obvious to you that the LCD, the least common denominator, is 2x squared. So the first fraction, to get a denominator of 2x squared, I have to multiply the numerator and denominator by x squared. The second fraction I don't have to touch. The denominator is already 2x squared. In the third fraction, 1 over x, I'd have to multiply the numerator and denominator by 2x. Right, now every single denominator over here is 2x squared. So that's going to be the denominator of the final fraction. Then we have the numerators combined. 1 times x squared is x squared. Then you have minus 3. I'll put that at the end. And then you have minus 1 times 2x is 2x. So minus 2x there. It's greater than or equal to 0. So now I have what I want. Single fraction on one side, 0 on the other. And I can do some factoring, right? The numerator factors to x minus 3 times x plus 1. Denominator is just 2x squared. And then we have is greater than or equal to 0. The critical values, the values that make the numerator 0 are positive 3 and negative 1. And the only value that makes the denominator 0 is 0 for x. I mark these on a number line. So we go negative 1 on the left, then 0, then 3. And see which of these, are solutions. Now 0 isn't because it makes the denominator 0, so I put an open point above 0. Now 3 and negative 1 are solutions, right? They make the left side 0, and 0 is greater than or equal to 0. It satisfies the equal part. So negative 1 is a solution, positive 3 is a solution. All right, then I test values in each of these 4 intervals broken up, by the 3 critical values. Left of negative 1, how about negative 2? So in the factored form here, you'd have a negative times a negative, which is positive numerator. You'd have a positive denominator because of the square there. That'd be a positive number on the left. Is that greater than or equal to 0? Yes. Right. Yes, it is. So the numbers to the left of negative 1 are solutions. But between negative 1 and 0, a nice number there would be negative 0.5, negative 1/2. You'd have a negative times a positive. You'd have a negative numerator and a positive denominator. You would have a negative number on the left. And is that greater than or equal to 0? No, it's not. So there are no solutions between negative 1 and 0. Leave it blank. Then between 0 and 3, how about 1? Now you'd have a negative times a negative numerator, and positive denominator. You'd have a negative number on the left. Again, is greater than or equal to 0? That's false. So the interval between 0 and 3 is also blank. And then to the right of 3, how about x equals 4? Positive, positive, positive. Everything's positive on the left, so you have a positive number on the left. Is that greater than or equal to 0? Yes, it is. So all the numbers to the right of 3 are solutions, right? So the only numbers that are solutions here are to the negative 1 and to the left of that, and greater than or equal to 3. So interval notation, the first piece here is from negative infinity up to negative 1, always parentheses on the infinities, and a bracket on negative 1, right? It is a solution. Then we have a gap. Now, this hole is really technically not there, right? It's another hole. It's an empty space. So this whole thing from here to here is the gap in the graph. So the next one I start, so again, a union symbol to represent the gap, or, right? And then the next piece of the picture starts over here at 3. We go from 3 to infinity. Bracket on the 3. 3 is a solution, and parentheses on infinities. And there you go. There's the interval notation for the solution set of this inequality. Great. All right, so now we're going to get back into a couple easier ones. These are like some problems from earlier where you had a single fraction on one side, 0 on the other already, and then I just did some factoring. So this fraction, it's already a single fraction on one side, 0 on the other. I'm just doing factoring, right? So x squared minus 16, that factors to x minus 4 times x plus 4. And then we have is less than 0. The critical values here, right, the CVs are 4 and negative 4. Right, those make the denominator 0. Nothing makes the numerator 0. I mark these on a number line. Right, negative 4 would be to the left of positive 4. Neither one of these would be solutions because you have a denominator of 0. So open points above those. And then I'm testing values, right? So how about x equals negative 5 for the values left of negative 4? Well, the numerator is always positive, and both factors of the denominator would be negative, or you'd have 25 minus 16, that'd be positive. Positive numerator, positive denominator, you have a positive number on the left. And then is that less than 0? Nope. So leave that blank, that interval. Between negative 4 and positive 4, how about x equals 0? You'd have a negative number on the left. Is that less than 0? Yes. So the numbers between negative 4 and positive 4 are solutions. And then to the right of 4, how about x equals positive 5? Well, same thing. I'd have a positive number, 25 minus 16, you'd have 1/9. You'd have a positive number on the left. Is that less than 0? Absolutely not. So the only solutions are the numbers between negative 4 and positive 4. And the interval notation for that would be, the negative 4 comma 4 there with parentheses on both, because again, they're not solutions. So there's the interval notation describing the solution set of that inequality. Example 30, very similar, right? Already a single fraction on one side, 0 on the other, like I like to start with. Do some factoring. We have 4 over x minus 5 times x plus 5, and we have is greater than 0. The critical values this time are 5 and negative 5. Right? Those make the denominator 0. I then mark those off on a number line. Right? Negative 5 is to the left of positive 5. Neither one of those would be a solution. So open points over both, right, because they make a denominator 0. And then I test some values. To the left of negative 5, how about negative 6? Well, you'd have a positive numerator, positive denominator, because it's a negative times a negative. So there's a positive number on the left. Is that greater than 0? Yeah. Positive numbers are greater than 0. So the numbers to the left of negative 5 are solutions. How about between negative 5 and positive 5? Well, 0's in there. Let's pick 0. Now the left side would be a negative number. Is that greater than 0? No. So that's a blank area. And then how about to the right of 5? Plug in positive 6. Everything's positive on the left. So you have a positive number on the left. Is that greater than 0? Yes, it is. So all these numbers to the right of 5 are solutions. And there we go. There's a picture of our solution set, a nice graph. And we can easily write the interval notation. Right? We have from negative infinity up to negative 5 with parentheses around those. A gap, right? Union symbol for the gap, or the or. And then from 5 to positive infinity. And parentheses around those. Okay, there's the interval notation for the solution set of that inequality. Alright, and then the last couple is where I'm going to do some subtraction. Remember, I want 0 on one of the sides. Right. So same deal here. I want to get 0 on one of the sides, so I'll just subtract one of the sides to the other side. So we have 4 over x minus 2, then minus this other fraction, 3 over x plus 1. And then that's greater than or equal to 0. So now I have a 0 on one side like I want, and then I'm going to do some subtraction. I want to get these to be a single fraction. So I need a common denominator. Now I'm hoping it's obvious what the LCD is here. Just be x minus 2 times x plus 1. So for this first fraction, I need to multiply the numerator and denominator by the quantity x plus 1. And the second fraction, I'd need to multiply the numerator and denominator by the quantity x minus 2. I'm hoping that's obvious. So the denominator will be this common denominator, right? It'll be x minus 2 times x plus 1. And the numerator, I'm distributing the 4 here and distributing the negative 3 here. Right? Don't forget that. Negative 3 times the x minus 2. So I'd have 4x minus 3x, that'll give me 1x. And then plus 4, then negative 3 times negative 2 would be positive 6. You have positive 4 plus 6, that'd be positive 10. Alright. Okay. And So that's the numerator totally simplified. And greater than or equal to 0. And this fraction is also, in the numerator and denominator are factored. And so I have what I want. Single fraction on one side, 0 on the other. It's nice and factored. Numerator and denominator are factored. So now those critical values are easy to state. Right? X equals, negative 10 would make the numerator 0. And then positive 2 and negative 1 make the denominator 0. Right, so those are the critical values. And I mark them off on a number line. So the values of x. Negative 10 would be furthest left, followed by negative 1, and then positive 2. See which ones are actually solutions or not. Now negative 10, when I plug that in, 0 on the left is greater than or equal to 0. That's true. So negative 10 is a solution. But negative 1 and positive 2, those make the denominator 0. So those can't be solutions. Right? So open points on those. Can't have denominators of 0. And now I'm going to be testing a value in each of these 4 intervals. Right? So to the left of negative 10, how about negative 11? Well, you'd have a negative numerator, and then in the denominator you'd have negative times negative or positive. So negative numerator, positive denominator, that's a negative number. And is a negative number greater than or equal to 0? No. Right, so no solution to the left of negative 10. Right. Okay, how about between negative 10 and negative 1? So let's say negative 2. That's between negative 10 and negative 1. You'd have a positive numerator, then a negative times a negative again, negative 4 times negative 1. Positive numerator, positive denominator, you'd have a positive number on the left. Is that greater than or equal to 0? Yes, it is. So there are solutions between negative 10 and negative 1. Now, how about between negative 1 and positive 2? Well, 0's in there. That's an easy one to pick. Now, when x is 0, you have, positive numerator. You'd have a negative denominator because there'd be negative times a positive. Positive numerator, negative denominator. You'd have a negative number on the left. Is that greater than or equal to 0? No, it's not. So no solutions between negative 1 and positive 2. And then to the right of 2, say 3. Everything's positive now. You'd have a positive number on the left. Is that greater than or equal to 0? Absolutely. Right. So the values to the right of 2 are solutions as well. And there we go. We have a picture of our solution set there. And let's write the interval notation for it. So going left to right. Now this first piece goes from negative 10 to negative 1. So I have negative 10 comma negative 1. Negative 10 will get a bracket on it since it is a solution. Negative 1 gets a parentheses on it since it's not. Then there's a break in the graph, a break in the picture, a gap. We usually represent that right with that union symbol. And then from 2 to infinity for the rest of it. Right? 2 to infinity. Parentheses on 2, it's not a solution, and always parentheses on infinities. So here's the interval notation for the solution set of that inequality. Wonderful. All right, and then last but certainly not least, finally, example 32. All right. So once again, I don't have what I want. I want everything on one side, 0 on the other, and then make that one side a single fraction. So I'm going to subtract the 4 over x plus 2. So we have 5 over the x minus 1, and then minus 4 over x plus 2, and that's less than or equal to 0. So I have 0 on one side, fantastic. Now I want to put this other side as a single fraction. We're doing some subtraction now. So in order to add or subtract, I need a common denominator, right? The LCD, I hope is obvious, is x minus 1 times x plus 2. So in order to get this to be the denominator of both these fractions, the first fraction, I'd have to multiply the numerator and denominator by the quantity x plus 2. And then this second fraction, I'd have to multiply the numerator and denominator by the quantity x minus 1. Right, so now both of these have this LCD as the denominator. So when I subtract, right, that'll be the denominator, right? X minus 1 times x plus 2 will be the denominator. And then in the numerators, we're combining like terms. I'll distribute the 5 to this x plus 2. And then don't forget the minus. I'm distributing the negative 4 to the x minus 1. So we have 5x minus 4x, that'd be 1x. And then 10, 5 times 2. And then negative 4 times negative 1 be plus 4, positive 4. 10 plus 4 be plus 14 in the numerator. All right. And this is less than or equal to 0. Okay. Now I have what I want to start. Single fraction on one side, 0 on the other, and the numerator and denominator of this fraction are already factored. So then those critical values are easy to state, CVs, right? The value that makes the numerator 0 would be negative 14. The values that make the denominator 0 are positive 1 and negative 2. And I put these critical values on a number line. These are values of x, and the furthest left would be negative 14, followed by negative 2, and then positive 1. And then I see are these solutions or not. Now negative 14 would be, because if I plug in negative 14 for x, you'd have 0 on the left is less than or equal to 0. 0 is equal to 0. So that satisfies this. So negative 14 is a solution, closed point above that. Then the other two values, negative 2 and positive 1, those make the denominator 0. So that's bad, right? So open points on those. Right? Those are not solutions. And then I test the intervals around these, right? So to the left of negative 14, how about negative 15? Well, you'd have a negative numerator. Then the denominator, you'd have a negative times a negative, which would be a positive. So negative numerator, positive denominator, making the number on the left side a negative number. And then you have is less than or equal to 0. Is a negative number less than or equal to 0? Yes. So these numbers to the left of negative 14 are solutions. And I'll mark that off. Between negative 14 and negative 2, how about negative 3? I'll test that. All right, when x is negative 3, the numerator is positive, and both these factors in the denominator are negative. But a negative times a negative would be positive. So you have positive numerator, positive denominator. There would be a positive number on the left. And is that less than or equal to 0? No. So leave that blank, that interval. All right, then between negative 2 and 1, 0's in there. That's an easy number to test. You'd have a positive numerator, and then negative times positive, a negative denominator. That would make the left side a negative number. And is a negative number less than or equal to 0? Yes, it is. So there are solutions between negative 2 and positive 1, right, where the 0 came from. And then to the right of 1, let's just pick 2. Right. And you'd have a positive numerator, everything positive on the left there. You have a positive number on the left, and is a positive number less than or equal to 0? No, it's not. So there you have it. These in the picture here, these ones I marked off, are the only solutions, right, of this inequality. And you can check, pick any of these numbers you want. Take any number from negative 14 or less, or any number between negative 2 and positive 1, and plug it into the inequality, and it should be a true statement. And then the interval notation, right, you have from negative infinity up to negative 14, right, always parentheses on the infinities. And negative 14 is a solution, so I got a bracket on that. Then we have a gap, right, space, so union. And then the next piece, we're going from negative 2 to positive 1, so negative 2 comma 1, and neither of those are solutions. Right? Negative 2 is not a solution, 1 is not a solution, so parentheses on both of those. And there we have it. Right? There's the interval notation for the solution set of that final inequality. All right. So you notice I did the same thing every time. Got everything to one side, 0 on the other. Got the one side with everything to be a single fraction. Factor the numerator, factor the denominator. Didn't cancel anything. Didn't multiply by the LCD. Listed those critical values. Put them on a number line. Determined which ones were solutions and which ones weren't. And then I plugged in a value from each interval on the number line to see which intervals had solutions, and then you finally wrote the solution set in interval notation. Always going left to right. So yeah. Hopefully watching me go through these 32 examples helps you out when you're working on similar problems. And thank you for watching.